Hi everyone, my name is Amélie Gruel and I'm a PhD student at IMSE-CNRS, a French laboratory. Today, I will be presenting you our article on the performance comparison of DVS data downscaling using spiking neural networks, recently accepted at WACV 2023. This work was developed with my supervisor Jean Martinet and with Bernabé Linares-Barranco and Teresa Serrano-Gotarredona², two microelectronic researchers at IMSE in Spain. Our main contribution is the implementation of an innovative method to downscale spatially event-based data using spiking neural networks. First, let's define the terms we use. Event-based data is the visual output produced by the dynamic vision sensor, or DVS. It corresponds to the asynchronous activation of pixels only at the time of a change in brightness in a visual scene. Spiking neural network, or SNN, represents an asynchronous type of artificial neural network closer to biology than traditional artificial network. The joint use of DVS and SNN is a promising combination for dynamic visual data processing, as they share many features such as biological inspiration, temporal dimension, model sparsity, and aim for a higher energy efficiency. Spatial event data downscaling is a non-trivial and increasingly relevant issue, as embedded systems tend to use DVS and SNN conjointly, but are highly limited in energy resources, memory, computational power, and communication bandwidth. Indeed, energy consumption is directly proportional to the number of spikes processed, thus to the number of input events, itself proportional to the number of pixels. Finally, deep SNN models also face difficulties in handling heavy data. In this work, our core objective is to design a fully integrated energy efficiency SNN model able to run dynamically on a neuromorphic platform. We introduce in our work two novel SNN architectures using spike pooling to downscale events spatially. The input events are split into two batches according to their polarities in order to preserve as much as original data as possible. They are then translated directly as input spikes in two 2D layers connected to two smaller layers of the required downscale size using a one-to-one exciting convolution. In the first architecture, the two polarities are handled separately, although during the same simulation. The second architecture builds on the first one and adds a mechanism for mutual inhibition between the polarities using a one-to-one inhibiting convolution. Thus, spatially downscaling using SNN pooling relies entirely on the neuron's intrinsic dynamics, which come close to the behavior of a DVS pixel. We present in this work a quantitative and qualitative comparison of those two novel methods with the spatial event downscaling methods previously implemented by the TONEC library and ourselves. We compared two datasets, DVS 128 gesture and NMList, downscaled spatially using different methods and dividing factors. We compared physical properties, such as the mean number of events and the temporal density. We also reviewed the evolution of classification performance using the Slayer classifier. Finally, we studied the evolution of the runtime necessary to downscale 1 second of real-time event data. Here, both SNN methods run on neuromorphic hardware are obviously the closest to real-time. All in all, these quantitative and qualitative comparisons demonstrate that SNN pooling achieves an efficient trade-off between the optimization of physical properties, classification performance, real-time data handling, and energy consumption. If you're interested, you can take a closer look at our results in WACV proceedings or contact us directly. Thank you for your attention.